The student's t-distribution is a distribution that's similar to the standard normal distribution. We use it because without our population standard deviation, sigma, we cannot calculate a z-score. If you notice, we need that sigma in order to do our calculating. So we use this t-distribution in several instances to find a t-score. That's why it's called a t-distribution. These t-scores are very similar to our z-scores. Now, when do we use t? Well, remember when we looked at the central limit theorem, we saw that our magic number for sample size was 30. So the question was, well, what if your sample is less than 30? And what I said was, well, we can't use these formulas that we were looking at. We can't use z. We can use t, though. If you look at these three conditions, these three separate conditions, you see they all have in common that our standard deviation is unknown. Our sample is small and population is normally distributed. That's one condition. Or our standard deviation of our population is unknown and the sample is large. That's a second condition. Or our population standard deviation is unknown, the sample is small, and we either don't know anything about the shape of our population distribution or we know that it's skewed. So the t-distribution compared to our standard normal distribution, you see they do have several characteristics in common. They're both bell-shaped. The area under the curve is 1. The mean, remember that's at the highest point, has a t-value of 0 and a z-value of 0 in the standard normal distribution. If you look at the picture at the bottom of the page here, the t-distribution is a little shorter, and the tails actually are not as close to the horizontal axis. They're a little fatter. Now this formula here, how we calculate our standard deviation, it depends on something called degrees of freedom, DF. You will never have to use this formula here. That's compared to the standard normal distribution that has a standard deviation of 1. Now we are going to use our Desmos or graphing calculator to find our t-value in a similar way to how we found our z-scores. In general, t-scores are a little bigger than z-scores for the same amount of area. Now a t-score, we only need this degrees of freedom to look up, and the area. We need the degrees of freedom and the area to find a t-score. This degrees of freedom, df, is equal to the sample size minus 1. So df is equal to n minus 1. This df, degrees of freedom, depends only on the sample size because it's the sample size minus 1. Now, degrees of freedom can be described as the number of observations that can be freely chosen, and I will go over that in class at a later date. The way that finding the t-score works, we need to know the area, and we need to know either the sample size or the degrees of freedom. In this example, we know the degrees of freedom is 12, and the area in our right tail is 0.05. Well, if we're going to use Desmos, we have to choose the t-distribution and the inverse CDF. The area that it wants is the area to the left, so we don't put 0.05 in, we put 0.95 in. On the other hand, if you're using a TI-84, you're going to use the second var's choice 4, and again it asks for area to the left and a degrees of freedom. Here's another example. In this case, we know the area to the left is 0.025, and we have 66 degrees of freedom. So, like the previous example, we need to use t-distribution with the degrees of freedom in the parentheses, then a period, then inverse CDF with the area to the left, or your inverse t if you're using a graphing calculator. Now, the thing about t-scores is they are generally rounded to 3 decimals. Z-scores we round to 2 decimals, but t-scores we round to 3 decimals.